Okay, you told me that the midterm helped you to fix your senior design project. Tell us the story. Hmm. Hmm. I see. I see. I got it. I got it. So, and finally worked, huh? Finally. Yeah, okay. Good. So let's tackle the most important part of this course, which is PID controller. PID controller. Already we tackled the role stability criteria, both the dynamical system, first order, second order, nth order, stability, unstability, marginally stable system. So all its tools we're going to use in designing controllers. Okay. As I promised in the first class of this course, I'm going to stick to the super important example that I always teach in my classes, pendulum, particle pendulum, to control it by a control torque Q, and also I'm going to teach inverted pendulum, designing controller to control the position of that. Okay, that's why I told you that these two examples they are super important in designing controllers, but not now. Now I'm gonna go over the components of controller. Now you're expert of MATLAB and Simulink. I see that many of you in the midterm you did great. So now, so if this is the plant G plant of the system, and your plant is not doing well in transient response or in steady state response, so you need controller. If your system is unstable, make it stable. If the transient response is not good, to fix it. So you need C control unit. And why? Because you want to follow the input. What you want finally, you want y over x, output over input is almost 1. Output follows the input. This is the whole big picture of the control, even after graduation. If you go to grad school, you're dealing with the non-linear control, it's the same story. Okay? Story is the same. You want the output follows the input. Okay? So you know that this signal is a E error signal, right? This is unity feedback, meaning that the sensor is ideal, so transfer function is 1. And you know that this is U, the command coming out of the controller, going to the system to fix it. So this is control command. We generally say is control commands. Control commands. Okay. So as I told you, if U of t is just proportional, just a kp proportional of E of t, means that you're multiplying the error signal by a what? By a constant number, proportional gain. Proportional constant or gain. Okay, KP, proportional P. So if you apply the Laplace in the both sides, so U of S gonna be Kp in E of S. For what? For this unity feedback block diagram that eventually I'm gonna take it to the Simulink and then MATLAB by coding. On the other hand, if transfer function of U of S over E of S is Kp, a gain, proportional gain, your controller is named P controller. This is transfer function for P controller. P controller. Bear with me, I have too many things to talk about this. This is case 1, case A. Now let's go to case B. I'm gonna talk about that. What's the application of P controller? What is function in the system? So B, if U of T control command is dE over dt, means time derivative of error signal. Time derivative of error signal. So in that case, if you apply the Laplace transform from the both sides, you get U of S is, now you know what's the Laplace of derivative. What gives it? What it gives? You did it in the homework, in the midterm. I'm sorry. What's the derivative Laplace? Like as x dot. What is the derivative of this? Laplace is S x of S. That's right. Remember? This is gonna be S E of S. Because derivative gives you this S. So if U of S control command over the error signal is I'm gonna put, I forgot to put here, sorry, KD, sorry guys, KD derivative, D is for derivative. Let me write here. This is for derivative, D, derivative gain. So if that it is KDS, you have D controller derivative because you have S. Derivative gives you S. That's right. So this is D controller. D controller. Bear with me, I'm not done yet. Can I go to the next page? Yes, everybody? So, and C. Let me change the color. C. If control command in time domain is integration of error signal, now you know error signal final value theory, you know everything, right? Okay. So, and you apply, and obviously there is Ki here, gain, Ki integration. So if you apply a Laplace transform on the both sides, so you get, you know, that the Laplace of integration, you have in your notes, gives you 1 over S, remember? So U of S is gonna be Ki E of S over S. This 1 over S means integrator from Laplace transform when I was teaching you. So on the other hand, when the U of S over E of S control command over error signal is Ki over S, You have I in the controller, integrator. I controller. Okay. The question is why integration, why derivative, why proportional control? Why everything looking to the error signal, integration of the error signal, derivative of the error signal, proportional of the error signal. Let me take you back to the high school. You are graduating, but this is fundamental from high school. Suppose you have a function f of t over t, and it has a graph. What's the derivative at this point from high school? You tell me. What's the derivative? df, yes, exactly, over dt. Means slope here, right? So if you put your eyes, you put an eye here, this is your eye. And the slope looking this way, that's right. What do you see here? You see future, right? Future of what's happening. You see what I'm saying? Even the slope here, gonna be this future of what is happening. So derivative simply means future. Future of error signal. When I say U over E control command is KDS derivative, means I want to see what's the future of it. I'm predicting what is future of error signal, simply speaking. You got it what I'm talking about? Yes? Huh? Now, let me again stay at the high school. F of t, you have this point. At this point, t is equal to t naught. I want to see what's the integration of this. What's the integration from high school for a curve? What's the integration? What is exactly f of t dt is the area under the curve. Your friend said area under the curve means whatever is before this point. Before means what? Opposite to future. It is what? Before. What? Exactly, it's past. When I say my controller is I controller, Ki over S, means I'm looking at the past of the error signal. What happened for the error signal before this? You got it? Everybody? Now, can I go to next page? Now, when I say the controller E over U control command error signal is proportional, just a constant number. You tell me, you teach me. We had future of that. We had past of this. Now we have only multiplying by a number. Means what? P controller means present. Yes, present time. I want to see what's happening right now for the error signal. You got it? Simple like this. That's why PID controller is being used for 99% of all industrial units. Name it from the airplane to the turbine manufacturer to car manufacturer, and even in your home AC system, your car AC system, your car cruise system. Okay, because when you set the cruise system to 60 miles per hour, it's gonna send a command signal that is the fuel to the engine. Okay, that it's gonna see the past of error signal until it reaches 60 miles per hour. present, and gonna predict the future of it. Simple. So bear with me. I'm not done yet. Okay? But a good question. Okay? In the coding, I'm gonna teach you. In coding MATLAB. Okay? So now if I say U of S over E of S is PID, means KP plus KDS plus KI over S, this is completely PID control. Why I didn't answer your question? Because first I have to teach you what are the function of each of these. Okay? What gonna this do? What gonna this do? What gonna this do? Understand? So we understand. PID means past, now, future of the error signal. Because at the end you're gonna write U of S gonna be KP plus KDS plus KI over S in E of S. That's right. It's a transfer function of the controller. Look at here. That's what I plotted here. U over E. So right. U control signal goes to the plant. That's what I want to teach you from my famous. Every control professor famous example, pendulum. This is the frequency in the time domain. U of t in PID gonna be KP E plus KD E dot derivative plus KI integration of E dt. I just transformed to the frequency domain. Why? Because MATLAB Simulink can help us. Simulink actually can. When I do coding, I'm gonna stick to this. Exactly, I'm gonna type this line in coding of MATLAB. But in Simulink, I'm gonna do this. This is Simulink. This is MATLAB coding. Okay. You got that, everybody? Now, let me take you back to my lovely example to teach you the function of each of these. Then you can understand your question answer. Remember that in the first class, we did OD in MATLAB of this, we derived everything. Now I am adding controller. This is controller U, torque. Here controller is a torque, okay? This is particle, so mg, remember that we did, and this is angle theta, and this is the massless bar, and what we did, we said sum of the forces around point O is IO theta double dot. From dynamic course, I taught you this, remember in your notes? So, okay, moment around point O is only mg L sine theta is mg L sine theta and is negative. Why? Because I told you this is, I taught you 10 times. This is increasing, mg torque gonna decrease that. Decrease means resisting. Resisting means negative. And because this is particle, I taught you gonna be L theta double, from dynamics. But now you have what? You have control torque. We have a torque here. U. See? U minus M. On the other hand, if it is ml square theta double dot plus mgl sine theta is equal to u of t. Remember? I'm dividing everything by ml square, so we have done once before this. I'm just refreshing your mind. G over L sine theta is 1 over ml squared. I'm going to exactly do this in Simulink, okay, after teaching you the PID function, u of t. Do you remember what was the name of this? I bet you know. What was the name of this for pendulum? Natural frequency square. Can I go to the next page? This is not dynamics class. I already taught you this. I'm just, now I added controller. I want to design controller. Okay. So you're going to have theta double dot plus natural frequency square sine of theta is equal to controller u of t. Remember that we linearized around the equilibrium point. You did in a midterm, right? Intentionally, I assigned such a midterm that we linearized around the equilibrium point of 0 state without any actuator. So you're going to be theta u of t. And now you know that assuming that theta at time 0 is theta dot at time 0 is 0, and apply the Laplace transform, you get theta of s square, theta double dot s square plus omega n square is u of t. So you get theta over u is 1 oh sorry guys, I forgot this. 1 divided by ml square divided by ml square and you get theta over u, real theta, outcome to the system. Output over the control command is 1 over ml square s square plus omega n square. Bingo! You have seen this before in the first class. Now I'm going to take it back here. Here we go. So here is theta output. This is desirable input, desirable angle that I want to keep. Say for the pendulum, I want to keep it as 45 degree, pi over 4. And this is real output. This is theta over u, over control command, u. This is u. Theta over u is 1 over ml squared divided by s squared plus omega n squared. Open loop transfer function. See? Theta over u. You got it, everybody? Yes? Yes? Now you tell me, this open loop transfer function, or G, that we know it, now you know it, open loop transfer function, we name it as G. How many poles it has? How many poles it has? We have done this many times. How many poles it has? 2 poles. P1 and 2, obviously from kindergarten, is plus minus I omega n. A pair of pure complex, a pair of pure imaginary poles. If you plot this on the complex plane, as we have done several times, it's going to be here. Here we go. And you know that if the poles are on the imaginary axis, how your system going to behave? Tell me, I taught you. Stable, exactly, marginally stable. Marginally stable means if you plot theta after linearization versus time As you know, it gonna oscillate forever. But this is not good because your boss asks you to keep the pendulum at 45 degrees. Your boss wants this from you. As a rover on the Mars, robotic arm is like this, say, simplified. I want to keep this at, when rover is moving, say, for example, theta d, I want to keep it as 45 degree or pi over 4. I need a controller from you to make this happen. Okay? Can I go to next page? So I need a controller to move these poles to the left-hand side, to the stable, not margin stable. Okay, so let's do that step by step. Suppose that you are teaching to your boss, he got bachelor in business and has no idea what is control. You say, you know what, boss? Okay, I'm gonna design a P controller. Remember? P controller, U over E, as I taught you now, is KP. This goes to my open loop transfer function of 1 over ml square s square plus omega n square. I want to design that. Let's see what happens, Theta d, theta, real. So, you know, if I do that, you get theta over theta d, closed loop transfer function, which is y over x, remember previously? Gonna be this multiplied by this, your open loop transfer function gonna be this. Gonna be kp over ml squared divided by s squared plus omega n squared. 1 plus, again, because this is your new g, that's right? Now you know it. I taught you. This is your new g. It is g 1 plus g. And again, kp over ml squared s squared plus omega n squared. So closed loop transfer function, after designing this P controller, after simplification, for God's sake, gonna be kp over ml squared, and here s squared plus omega n squared plus kp divided by ml squared. Interesting, right? What did P controller? P controller added to the natural frequency of system. For simplicity, I assuming m is 1 kilogram and L is 1 meter for the pendulum. So this is gonna be kp s squared plus kp plus omega n squared. So now you tell me, what are the poles of the closed loop system? This is, in the previous case, without controller, we had plus minus I omega n. Now, here your poles after adding P controller gonna be this plus minus I omega n squared plus kp. What happened for the natural frequency of the system by adding a constant number? What happened? Natural frequency increased. Means you did this ridiculous act. Look at here, guys. Poles was here previously. By adding P controller, you did this. You added the frequency of the system. Physically meaning, by only adding P controller, Originally, the system was this. By adding P controller, you did this to the system. Is it good? No, it's not. Because you want to have this. Your boss said, I want to have this mic, Elizabeth, 45 degree. Won't you give me this? But you didn't fix the problem. You only added to the natural frequency of the system. That's why sticking to this example to visualize fundamentally what is PID control. Now you say, okay, boss, give me a second. Let me try PD controller, derivative proportional. Kp plus kds to the pendulum. This is going to give you U, that's right. And here is E again. Control command to the pendulum. So pendulum was, because I assumed M is 1 and L is 1, right? So this is here gonna be 1. See, here gonna be 1. I'm just 1 divided by S square plus omega n square. Now you're gonna say, boss, let's see by adding D controller, what happens to the system? Until this point clear? Yes, everybody? We added P controller, I'm writing here, important. P controller affects transient response. How? Because you saw that changed natural frequency on omega n. Okay? For this example. Now, we have to find theta again and over theta. This is PD controller now for the pendulum. This is gonna be, if you do that, I'm just simplifying my mind, okay? It's gonna be S square plus KDS plus KP plus omega n square. Oh, good. Guys, stop writing. I want to ask a question and give me the answer. After adding the P controller based on the Rolf stability criteria, is this system stable or not? What was the first condition? All coefficients exist and be positive. What we are missing here? What we are missing here? Yes, we need S. We miss S term. It's 0S. So it says your system is not stable. Now you say, okay, by adding E controller to P, we got that missing term. Bingo. You see? Huh? And if you remember, generally speaking, when I was teaching you the second order system, general form you have in your notes was like this: S squared plus 2 zeta omega ns. Remember this, everybody? Yes? What was the name of the zeta? You tell me. What was the name of the zeta? Yes, damping ratio. So you see that the controller adds damping to the system, physically speaking, in reality. So take home message is this: the controller adds damping to the system. Good. We were missing damping, and because of that missing damping, we were oscillating forever. You got my message? Huh? So now theta over theta d for the pendulum was Kp plus Kds, because I have to work on this. S square plus Kds plus Kp plus omega n square. Obviously, based on whatever I just taught you, this is your new natural frequency of the system, nu. And this is your 2 zeta omega n. Obviously, you have two roots, two poles, second order, and you see added a 0 to the system. 0 of the system is this. 0 is minus Kp over Kd. I'm going to plot on the complex plane. You see, I'm combining reality, physics with mathematics to give you better vision of what is control that you are just passing. So we added a 0 in the left-hand side, say here. You're showing 0 by a circle. This is convention. And we have two poles. But what two poles? Poles are this. Your boss says, Elizabeth, Mary, Mike, I want that you design a controller as a robotic arm of rover on the Mars. Be critically damped, not underdamped. This is a robotic problem. Okay? Why? Because underdamped, remember when I was teaching you, has an overshoot oscillation. I don't like it. This is robotic on the Mars. I want that you give me this. So when your boss says avoid oscillation, transient oscillation, now you have the tools from my class saying, oh, critically damped system means zeta is 1. Bingo. Look at here. I'm helping you to determine KD. See the whole story I'm now teaching you? Yes? Everybody? Critically damped system means zeta is 1 based on whatever I taught you. And your boss says, you know what, Elizabeth? I want that the natural frequency of this be 1 radian per second. Okay, good. These are the numbers your boss gives to you. You're going to say, I got it. 2 zeta omega n is Kd. As I'm not blind, I see here. And natural frequency is 1. Okay? Let me say, not 1. 12. Make it sensible. 12 radian per second. Okay? So your natural frequency is this. Kp plus natural frequency of pendulum, physical, is 12. Okay? So Kp, natural frequency, I'm going to take you back to here. Where is that? Natural frequency is called G over L. G is 9.8, almost 10. L is 1, is equal to 12. Say, oh, I found KP. KP must be 2. You got it? Yes? And now from here you get KD is 2 multiplied by 1 multiplied by natural frequency 12 is 24. Bingo. Bingo. Just now you designed a PD controller with me. On the other hand, you're gonna say to your boss, boss, let me take you to Simulink and I tell you my controller is 2 plus 24. Yes. This goes to, I said M is 1, L is 1, S squared plus omega n squared is 10, because 9.8 is 1. 9.8 almost is 10 squared for the pendulum. And this is what you want, 45 degree. And this is that. Here we go. Boss, this is your PD controller with these gains. PD. PD. We got it, everybody? Yes? Now, before going to the Simulink to run this, actually there's a mistake here, guys, because the natural frequency is square. This must be root square of 12 because I have no knots. I'm thinking that this is square. This is square. This 12. Sorry, guys. So your natural frequency of pulse is root square of 12 radian/second. Okay. If that's the case, this also must be this, and I have to fix this, guys. Sorry. It's gonna be 4 to the square of 3. So here I have to fix that. This is 2, 4 to the square of 3. Here we go. Okay. So you saw that the D controller added damping to the system, zeta. But remember, when you had overshoot, you have your notes was minus zeta pi over 1 minus zeta squared in percentage. Remember? When we had underdamped system was this. So you see that D like has P, another function is to modify, I'm teaching, transient response like P controller and stabilizes the system, because look at here, this stabilizes the system by adding S here. So now you learn that the PD controller, they are tuning transient response, modifying transient response, and P controller stabilizes the system at the same time. We got it, everybody? Yes? So Let me double check the number before going to the Simulink. Is 12. So Kp plus is omega n is square 12. It's gonna be 10. Yep. Kp2. So Kd is 2 multiplied by 1 by omega n. Yeah. 4 coming out. This is good. This is good. Now let me take you to the Simulink for your first design PD controller. It was clear, guys? Yes? Everybody? Any questions? It was clear?
Yes.
Good. So I built everything based on real example of the pendulum as a single 1 degree of freedom robot. Okay, so let me open a Simulink file from class over here. Second order. Yeah. Second order. Bolden, I don't care. I hope that I'm right with the numbers here. This is 10 to, yeah, okay. Pause this. So, I'm gonna, okay, good. Okay, I'm gonna copy and paste this to new. Okay, here. So, I'm gonna delete all of these. So 45 degree means pi over 4. I'm doing pi over 4. This is my pi over 4 in radian. That's right. Here we go. Stop. So we got this is desirable input. So this is open loop transfer function without anything. So gonna be s. What is this? So gonna be s square 0s plus omega n square 10 for the pendulum. This is pendulum transfer function. Oh, 0. Here we go. Okay, we got that. Now I'm gonna add PD controller. PID. Just type it here. Here we go. I'm gonna before embedding PID, let me save this, and I'm gonna see PD controller pendulum. And if I run this, as you know, I expect what? I expect forever oscillation. Come on, as you see, obviously, because I have a pair of pure poles. Now, as you saw, I'm gonna add a PD controller here. Just double click on this. Now you know how it works. So there's no I yet, I didn't teach you. The P was 2, that's right. And here was 4 SQRT of 3. That's right. The D gain, that's right. It's D. Can you double check? Check. Yeah, 2, 4. Yes. So D is this, and this is this. And I'm applying that. And here we go, bingo. Okay, and then I'm gonna just take this down to make it beautiful. And I don't need this. Only one is enough. Okay, and I want to just compare output with oh, so yes, I'm gonna make it 2. Output with input, that's right. Here we go. I'm gonna take it down. Was recording? Yes. Okay. I'm gonna save this. Now it must gives you what your bus wants. Typically. Oh, okay. So it changed, guys, from marginal stable, okay, to a stable system. But does it goes to the input? The input is this is output. So we have an error signal here, guys. Why this happens? From marginal stable forever oscillating, we change it to stable system with overshoot, but we have huge what? Huge offset error signal here. What was wrong with that, guys? What do you think? Okay, let's try it. I'm just following your orders, huh? I'm saying 15. You mean this? 10? Yeah, okay. 10, huh? Here we go. It has a mathematical reason. Okay. So let me more push it. Say 25 and 35. We are getting closer. Okay. So we have the reason, guys. Let me teach you that. So your new open load transfer function is this. That's right. After designing controller, this is your new G. I'm just putting the parameters G. You got it, everybody? Huh? Now I'm saying, what is ESS? Is limit of S x of S 1 plus new open loop transfer function after designing controller. Remember the final value theory. Remember it when time goes to infinity. After you design the controller, your input to the system is pi over 4, or step is gonna be pi over 4 divided by S. That's right. Step input, that's right. 1 plus Kp plus Kds divided by S square plus omega n square. S goes to 0. See, this is your designed what? Controller as an open loop transfer function. This S with this S goes to hell. So the error signal gonna be, for this specific example, which is power 4. So 1 plus this 0, this 0. Kp over omega n square. S goes to 0. So you're gonna have pi over 4 omega n square, that's right, in Kp plus omega n square. What your friend said has a mathematics behind. Here we go. Omega n of the system is constant. We cannot change it. Remember? It is G over L. Remember? G over L. So if you increase Kp, as your friend said, your error signal decreases. So you have to select, as your friend said, Kp a large value to make this a small value. See what happened? Everybody? Yes? You got it? Why that happened? So if I go to the model, I'm gonna keep it at 4 SQRT3. I'm gonna make it at 4, not 2. Now if I run it, doesn't change too much. So I have to go to, I'm gonna tell you why. This, here we go. See, coming up, okay? Based on the mathematics of finite value theory. Now I'm going to 16. We can use that mathematics to make it very small. Not too much. Let's say 25. Okay, going up. Then you can increase as much as you can. Say 50 this time. There we go. Or, bear with me, don't leave. I have a comment. Say 90. Okay. Almost close, but you can increase more. But we have another problem, guys, now. Your boss said critically damped system. We have an overshoot here. What do you have to do with this? What do you have to do with this? I want to have this one, this profile, guys. I want to have this profile. First, let's fix this P. To 250. I'm going to talk about this now, okay? Here your art comes. Okay, this is very close. But you see, you have more oscillation. Here, you need to add damping to the system. What was the damping? D part. So I'm going to increase to 20. Got here, guys? You have to play with the numbers to make that happen. Oops. See what happened? I added damping to the system, to the D derivative. I'm gonna add more. I'm gonna put this 50. See? Here we go. We are getting close. And now, what I'm gonna do, I'm gonna do this 500 and 100. Here we go. We are getting very close. But you have to fix this again. So you need more damping here because you have a little overshoot. We don't like that. Okay? So this is you. Based on the experience, you have to do that. For example, I can do it 200. So this is very close, but it's increased actually. You have to just take it down because this becomes so more noisy. Don't remember, decontroller adds noise to the system. Let us put it at keep 50. Okay. Yeah, it's coming down a little. If it decreases a little more, it's coming down, yeah, eventually. So now you are very close to target. Very close to target. From margin stable system, you made stable. You did this by PD control. You saw the mathematics behind it. Why you increasing KP? And we named high gain. If you put this high gain, E goes to 0. You got it, everybody?
Yes.
So we saw P and D, but I'm gonna teach you next class. I didn't teach you I, that's why I played with PD here. When I teach you I, maybe we don't need to change P and D. We have to stick to our what? To our original design. I'm gonna continue next class. These two numbers. Because I function control is to remove steady state error signal. So if I add I, I'm going to stick to this. I'm going to show you based on whatever we designed by the numbers correct. And the I going to fix it. We don't need to play with the KP. Okay? Hopefully next class, I'm going to finish this and send it to you. This code. And hold on.